All right, so how you guys doing today? Here, it's Monday. All right, so let's start. So I don't know if you guys all watched the previous video on YouTube channel. We actually now in the middle of chapter 7. The last one I taught, like the last Friday lecture, was the E and Z configurations geometry system. So unlike the trends, you can say system trends. Okay, you have also E and Z configuration. So this is sometimes more useful to identify a compound with this geometry system. So I can give you one example here. So if you have the double bond, obviously it's alkene compound, but they have some substitute arguments here. You can try to So whenever you have this alkene compounds here, you try to rank your substituted groups on the same carbon. So meaning you have to kind of divide this in a half and half, like left and right. So you can compare the priority of these two on the same carbon. So you're comparing these two, not these two here. So this is that. So in here, to rank the priority of each substituent group on carbon, you're going to use Cunningham in preload convention. So obviously, if you write this one more precisely, this is what it looks like. So obviously, carbon is higher in atomic number than hydrogen. So this one is higher priority than this one. So this is relatively speaking lower. So you're done with this part here. So if you look at this carbon here, you can see this one is also, let me do this one. If you redraw this one again more precisely, this is the way it looks like. So you have the same element, which is carbon, on here, this carbon. So it's kind of a bit trickier. But what you need to do from here is go one further away from the same carbon. So you have oxygen, oxygen here, hydrogen, hydrogen, oxygen. Whenever you have a double bond, it's pretty much the same, kind of going preload convention. So you count these as two, so the two oxygen, and there's another one over here. This one is oxygen, hydrogen, hydrogen, so OH. So because these two, this is high, but those two, this is higher in atomic number than hydrogen. So this is still higher priority than this one. This is lower. So if you look at this double bond here, and it's like this is based on this the double bond, where you can find the double bond. If these higher ones having the same phase, like this way, the low ones in the other phase, we're gonna call this resonant Z configurations compound. If it's not, so maybe you can have okay. So I'm gonna just do the same, right? So this is a higher, right? Lower, higher, and lower. Because you're comparing these two on each side. Okay. So in this case, you actually have a higher groups, high priority groups are opposite direction, opposite side, opposite position, lowers as well. In this case, we're gonna call this E, the Tadigan configuration. So obviously, this will avoid some type of confusion you may see with the cis and trans isomers. So sometimes E and Z is better system you can apply. Okay? So this is what we left last Friday. So I'll move on. Makes sense, right? So I'll just move on. This is a quick review. Okay. So there's one more thing that I kind of want to remember for the exam. So this will be the exam for sure. So please remember this one for the exam because it's very important in chapter 7. So whenever you have alkene groups here. This is a tetra substitute alkene, okay, here, and we have tri. Okay. We have di. We have also another ones on cis position. Configuration. It's almost same. It's slightly. This is slightly more stable, but anyway. And then obviously mono substitute. And there's no substitution groups on. Sorry. So here's the thing. You see this symbol here, meaning the stability. Stable stability. So if it's more substitute on your double bond in carbons the double bonds, you consider it as more stable. This is why I chose this one as the most stable. And there's no substitute group or very a low number. It's the least stable. So this is what I want you to remember. So you see this R here. It's just any RQ groups, any like a carbon chain, or any groups of organic groups will represent the in general R groups here. This is more substituted with the R groups. You will have a very stable form of alkene here. So this is what I want you to remember. So here's the thing. I'm going to explain why it's more stable with the more numbers of the substitution group, but you don't have to know for the exam, but only for your understanding. So the first reason is the hyperconjugation. So hyperconjugation is kind of a bit of a weird term that we use. This is kind of a bond elongation between pi bonds and also kind of a sigma bond and other carbons. So I'll draw in the picture. It may be more understandable. So as you know, this is in double bond, right? So that meaning they're in sp2, not sp3, right? So if you think about sp2, it's not on the tetrahedral structure anymore. I mean, molecular geometry-wise, they're going to be in like a tetragonal planar, right? So those carbons here and here are going to be on the same plane. Makes sense, right? Because it's a planar. So if you drew it from the lateral view, we feel like here. This carbon here. So there's another carbon here, but I'm gonna ignore it here. But you see this? This is double bond, and this carbon are on the same plane. Okay? All here. So if that is true, but this carbon here is a tetrahedral structure here on this carbon, but this is still planar. So this is kind of a little bit tilt on this side. But obviously these two have a double bond on the pi. Okay? So if that is the true, the hydrogen will have a sigma bond between carbon and hydrogen over here. They kind of somehow interact and elongate each other, but not very strongly, obviously. But in a position where you can see the position of the sigma bonds and the pi bonds and the carbon on double bond, they can somehow kind of conjugating simply means kind of combining into the one bigger one. So this will make the structure more stable. So this is the first reason why. This is what we call hyperconjugation. But you don't have to know for the exam. But it will probably make more sense in the picture. The second one is the orbitals, the bondings, bond orbitals. Okay? So that means I'll give you two examples here. So this is the one. Okay? So I'm going to ignore all the other hydrogen everything. Just bear with me. But this one is another one. Okay. then here's the, okay. Think about this one. So whenever you have, maybe we'll do one here. And here, this is sp2, but this carbon will have sp3, right? This is sp2. This will have sp3, sp3, right? Okay. So you know sp2 is a bit more stronger bond here. And also that makes sp2 to sp3 bonding stronger than sp3 to sp3. Okay. So if you look at this one over here, if there's only a hydrogen here, and there's no more carbon, we'll do the sp3 on this side of the double bond. But they can have those the sp2, sp3 bonds, which is somewhat stronger than sp3, sp3 on the both sides here and more. So this is also another reason why if you have a more substitute group on the carbon in a double bond, you're going to have a more stable form of alkene. But the I'll just move on. But I just want to remember this one. So maybe on your exam, it's actually quite a simple question like this one would be asked. So if I give you this is number one, this is number two. And maybe in the question, I'll ask you which one is more stable. And what do you think? It will be number one or two? Number one for sure, right? Okay. So because you have a tri-substitute groups on this the alkene group, but not. So by following this rule here, this is going to be more stable. So this is some kind of a problem you may expect to see on these. Okay, sounds good, right? So, but also try to remember this one. I will try to get to this one a little later today. So just try to remember. But it makes sense, right? We good. Okay. So just move on. So the next part, the second last part of your chapter 7 is the electrophilic addition reaction. Okay, so that simply means literally what it says in the word. So you just adding electrophile on the compound. So we call this electrophilic addition reactions. So one example I can give you is here, 2-methyl-2-protein here, plus hydrobromic acid over here. You're going to have some products here. And this like this. Okay. So you have those group added on this alkene groups. That's why we call this electrophilic addition reaction. We're just adding. So this is like an electrophile. This is electrophile. And you see, you guys all, some of you maybe watched the video the last week, right? So this is the double bond here. Would kind of behave like a nucleophile. So this is why we call this nucleophilic attack. Okay? Because it kind of behaves like a nucleophile, and it kind of grabs the electrophile. And by doing that, you kind of put this electrophile onto your alkene. That's why we call this electrophilic addition reactions. Makes sense, right? We good? Okay. So obviously, what you can do is you can do HBr. Also, you can do HI, HCl. That's all possible. In the form of hydrogen X, hydrogen form will be just all can be generally applied to this electrophilic addition reaction here. Okay, so there's one rule I want to tell you. So as you can see, you can have this one over here. Let me actually draw one more example here. Whenever you have, I'm gonna draw the same thing, okay? But with the now HCl. Okay? Let's do this one, the different one. Okay. So if you do this one, what you can have is two possible products here, which is this one. Okay. Right. Same, right? Same as we did for the hydrochloric acid here. And another one is what you can do. This one. Okay. So you have two possible addition on this position and this position. So this is two possible products you can estimate, you can predict from these two nucleophilic addition reaction here. If you look at those two, when you do the experiment, you get this is much more predominant than this one. What we found was the halogen groups were actually going to be placed where you can find the carbon is more substitute with R groups here. So, but not on the one with the less number. So we're gonna call this rule. We found this experiment results. One is much more dominant than the other. We're gonna call this mark of rule. Okay. So in this rule, it kind of explains why these are kind of a way it happens. So let me explain this one real quick. So this is so you're always that in this form of the reactants here, we're always going to this X group over here. We know what hydrogen will be on the more substitute carbon here. This is because of this one. This rule has published based on one reason is here, stability of carbocation. Okay. So this is where we can put the similar mechanism we applied just one before we talked. So if you look at this one here, with just one example here. Okay. This is the carbocation. There's another one. Okay. There's another one. Okay. And this one. Okay. So they are carbocation with the carbon with the positive charge right here. And then also it's surrounded by three substitute tri-substitute groups on here. So we're going to call this tertiary carbocation. This is the secondary because there are two, not with this hydrogen here. Okay. Secondary, number two. This is the primary, there's only one. Okay. One. There's nothing there. So it's pretty much the same what we did for the alkene groups here. For carbocation, if you have a more substitute or more R groups around on that carbocation, it's more stable. So stability order is like this way. So I want you to remember this one as well too. I'm also going to explain the reason why, but same here. That will not be on the exam. It's only for your understanding. So we have this stability order too because of the first hyperconjugation. It's pretty much the same what we did for the alkene. Only one difference is going to be the p orbital instead of the pi bonds. I will elongate it with this hydrogen carbon sigma bond because they're also kind of in the similar plane. But also there's a second reason why they're doing this is the inductive effects, or I can say induction. I hope you guys remember some part in chapter 2. They slightly covered the induction. Do you guys remember this? So induction is simply this one. If you have some compounds in here, okay, you have somewhat electronegative, quite highly electronegative elements in the compounds, and there's another one, and there's all the carbon and hydrogen here. So what you can do for this one is you draw all the structure over here, but this bond here, and orbitals, everything, it's not really. There's something actually linking these two. You know that, right? It's actually this bond means what? Just small 3D space where you can find the electron by high tens. That's all it really means. It's more electronegative, like an interaction there is like a very strong share in the same space, covalent bonds. It's more separated ionic bonds and so on. Anyway, so if you look at this compound in this way, they're not like in a more like a Lewis structure wise, but it's more like an electron club system wise. They're all kind of like linked somehow, even though they're somewhere around aware, right? And so this fluorine is not right next to the oxygen here, but somewhere in distance. But still, you think this whole as like an electron club system. Let's do it this way if it's working in here. You can try to draw in your head. And then this is more electronegative. So induction simply means their difference in electronegativity in the elements in the compounds. They make a shift. They make a bit of a way to electron more movements on this all kind of combined electron club system. So that meaning they're not going to steal electron from the other molecules down. That doesn't mean that they're going to steal the electron, but they're going to have a more pulling power, the electron in the other ones. So they kind of electron goes kind of in this, heading this way, right? So if that is true, oxygen itself is somewhat electronegative, right? So that means this one will have because of this one too, because electron going this way more on this side, this will have a much stronger pulling force to the electrons here. So then this hydrogen cation will be more easily, freely, more conveniently released from this compound. So by inductive effect, this, because it's fluorine technically, this will become stronger acid. Because this one, oxygen can dump this hydrogen cation more easily, right? So if that's happening, we cannot explain with the bondings, but this more induction kind of effect, that's what we call by induction. Makes sense, right? Somehow. So if that is true, think about it. If you have a cation around this the hydrogen, and also the one with the carbon group over here. The carbon is much bigger in size, right? And also a lot more numbers of protons and electrons here. So there are more. They provide more electron accessible environment for carbon cation than hydrogen. So that meaning they're going to have some electron. In the textbook it says electron donating. It doesn't mean actually they're giving the electron to here. No, that's not what it means. Like it's like inductive. Like it does not take the electron from the atoms, but it kind of more provide electron like a friendly environment for this carbon cation. That means this is a positively charged, but if there's more substituted like R groups, because of the carbon, relatively speaking to the hydrogen, that will give a more electron like a friendly, more like accessible environment for this central carbon cation. This will become more stable because this is a positively charged, but relatively speaking, it's all about the relatively speaking. Relatively speaking, there's hydrogen, carbon is better source of the electrons around this one, right? That is why if you have more associated with the R groups, we would have a more stable carbon cation. That's what we call index. Kind of makes sense, right? So, but once again, you don't have to know for reasoning. But this one I want you to know. This is what I want you to kind of remember. Okay, so if then this kind of makes sense, I'll try to explain one more. So maybe we can have some somewhat intuitive agreement on mechanical rules. Completely kind of makes sense here. So another one I want to talk about is the Hammond postulate. Okay, so this is the kind of something it will be really good if you can watch the previous video on YouTube channel too. But let me just do quickly review for you guys anyway. So this is an energy diagram. It tells the energy status of the compound over the chemical reaction. So maybe I can give you one here. So this is energy level of reactants here. And those two on the peaks, like the maximum points in this graph is what we call transition state. So maybe there's a two. Normally there's one, but now there's two. So this is the first one. This is the second one. So this is the first transition status. This is the second transition state. Okay? So you're going to have a first transition product here and like a second reactants to the final product here. So it's somewhere between, right? This is what we call intermediate. So it's just kind of somewhere in the middle. So if you do this one, now I can explain why it's happening this way. Yeah. Okay. This is the way this is the amount of energy you need to go proceed in a reaction. It's activation energy, delta G, with double dagger supercritical script. And between the two, or the second one here, is going to be, it's kind of hard to draw here, is the delta G. So for just this one, the first one, let's focus on the first one. This is going to be activation energy, and this is intermediate. So for getting up to this first step of the reaction here, this is the delta G, which is the positive. It's the free energy in the product is higher than the initial one here. So this is if it's positive, it's Indergonic reaction. Do you guys remember this or watch the video maybe? Okay. And if it's negative, it's exergonic reaction. Okay. So the Hammond postulate simply means this one. If you have the transition state, the transition state simply means the literary transition state. So you have a reactants here, you have a products here. The reactant to be products, you need to break the bonds in the reactants, right? You need to make a new bond to the products. So you can have a new product, right? You need to break the bonds, you need to make the new bonds to make the new compounds. That's how it works in the reaction. So transition is simply semi. So you breaking the bond in the halfway, you're making a new bond in the halfway at the same time. That is why, if you look at the transition state, it's very high in energy. So it kind of makes sense, because if you think about something in very high in energy state, it has to be very unstable. It is obviously very unstable because it's still during the reaction, which is only possible when it's really highly energetic and also unstable. This is why you see the transition state is very high. And also after first step reaction, it goes down. It kind of makes sense now. Okay? So this is the transition state here, and this is the final. For first step is product. We still call this intermediate, but for first step, what is product, right? So maybe it was only one step reaction. Could be stop here, right? So this is maybe intermediate here, but this is the first step product here. So if that is true, the Heyman postulate simply mean this one. Because of the proximity, your transition state energy and the product is, if it's endogaming reaction, when it's positive, if your delta T is positive, this is the structure of transition state and product is resemble each other. Okay? If it's an endogaming reaction, but if you have a exergonic reaction, so it's actually those two. It's actually this is higher in reactants and now lower in the product, so it's delta G is negative, right? So it's exergonic reaction. In this part, actually your transition state is more visible to reactants, not the products. It actually kind of makes sense because if you look at the energy diagram over here, your energy level on transition state is more close to the product here, right? So that actually kind of explains why there's a similar in structure. Because they're not that different in the energy level here. There shouldn't be much difference in between these two. But here it's very far away. So this is why by Heyman postulate, when you have an endogamic reaction, your transition state should be similar to the structure of your products. If it's exergonic, it has to be transition state compound structure should be similar to the ones in the reactants. So far, so good? We good? Okay. So if that is true, it actually kind of makes sense on the mechanical rule here. So if this is true, you better have to have a stable transition state to have a stable product, right? Makes sense? Because do you know the chemical reaction always happening to be in a more stable form? So if that is true, as you know, having carbocation here, okay, here is much more stable than here. So this is why. Let me draw into this one. This is why I'll show you. So in transition state, like I said, the double bond here is breaking. So I'm gonna put it like a dot line. There's new bond making over here, and also it's semi-forming, and also it's semi-breaking over here. Okay, so this is transition state. You see, this is why it's so unstable, right? But having this one is still better than this one because what? Stability of this carbocation. Okay? So this is more substitute carbocation than this one. This one is hydrogen. Right? So if you can keep this carbocation on this carbon in the double bond, previous double bond, you need to make the bonds on the hydrogen. The first step is hydrogen to this carbon. It's better to put this carbocation on this one. So in here, you're going to have this one, not this one. This is much more dominant position. They can do the reactions. So intermediate will be this one. Now, so intermediate will be carbocation for sure. Okay, so finally at here, it's going to be. So this is somewhat intuitively related to each other. That Markovnikov rule and also Heyman postulate kind of somehow explains why it's happening in one selective reaction, right? So if there is one specific product is more favored or chosen to be formed, we call this regioselective reaction. Okay? If there's two possible products, this one and this one, but it only prefers the one product much more dominantly, almost 99% or 90% sort of thing, we call this regioselective reactions. And also it is with the stability of the carbocation, also Heyman postulate, and that all kind of sums up to explain the Markovnikov rules. Some make sense. Some makes sense. Okay, good. So that is pretty much it. So whenever you do this, is only second transition state here, which will have this one. Now carbon cation is looking for something negative, right? So it's electrophile. And going to this is a nucleophile. We'll attack here. So now eventually, this final product very stable. It looks like this. So this is why this is the kind of desired product here, because of the position of where you can put the carbocation more stable with the more numbers of substituent groups or more R groups, so you can actually put the bromine where you can find the carbocation, which is here. So this is much more dominant product than this one. Okay, so this is the somehow kind of explains altogether. So I'm almost done. Let me treat it just one more time. I'm sorry. I'll treat it just one more time. But this is the last one for the. This is the last one for the chapter 7. Hopefully, I'll try to do very quick once more, maybe on Wednesday, if I move on to chapter 8, because it's kind of a lot of things to engulf at once. So I'll try to do it briefly at least on Wednesday, but this is the last one. So if you have this one, okay, 90 cyclohexane, we have maybe same this HBr, like the same like this form, right? And then when you look at the transition state, or the Y in the middle of the reaction, you have a two choice. Okay? Over here. So either this is where you can find the carbons in a double bond here. So you can have a choice to put the carbocation here or here. So here and here. And think about it. This one has one R group here. This one has two. Okay. So if this is 1 and 2, which one is more stable carbocation? Number 2. This is the 2 here, it's more stable. That's good. So if that is true, your final product will be more dominantly this one for sure, right? Okay. So I'll treat you one more. This is actually not dominant product here. There's some here, but actually the other one you can find is actually this one. So I know it's a bit tricky because this is happening because of this one. So I hope you guys just remember what I told you about the other ones. Try to look those compounds as like a whole electron cloud system. So what happens is what we call hydride skewed. So that means a hydride simply means hydrogen anion. So actually this one has 2 electrons, not 1. That's why it's negative because it's group 1 element. So the hydrogen means here. This is good actually. Good choice. You got the number 2. You didn't do it wrong. You did it right. Just you forgot to put the one more step, which we think kind of tricky. So if this is carbon cation here, obviously oil dominant on this position here. But if you look at the one on this position here, this is actually more substitute then this one even further. So what it actually do is you have a hydrogen over here, right? But this hydrogen with this whole group of pair of electrons move to here, right here. So it becomes here. And then the bromine anion attacks this carbocation. So this is quite dominant with some of this one, but obviously now you're not going to see much of this one. Obviously, no. This is maybe the worst choice, but this one is the best choice. So it kind of makes sense. So if you look at this one, it's like a Lewis structure, like I mentioned before. This will not understandable to you at all. But if you look at this one more like an electric cloud system, what it really happens is this one. You know, this is a better position for put the carbocation with the more substitute group in here. So, and this hydrogen now going to shift by doing this one. But in this way, they need to put the charge in half in here. Okay? So now they're shifting right in the middle, and eventually they go into this position here. And now you're going to shifting this charge fully, now half, and now it's fully on its way here. And then now it's more stable than even this one where you find the carbocation in here. So now you have a more stabilized carbocation in this compound. Now you have the next step to follow. That's it. That's it for chapter 7. Once again, I know it's kind of a lot of things to cover. I'll try to do it once more on Wednesday, and then I'll move on to chapter 8. As you know, chapter 8 is even longer chapter. So I'll try to do my best, but that's pretty much it. So thank you guys. I will finish here.